Pinball loss scores one quantile. CRPS scores the whole predictive distribution. You'll implement both in Python and know which one actually matches your forecast. After this, you'll understand how to assemble a pipeline that scores uncertainty and picks the loss, matching each forecast artifact. I'm Professor Pi, teaching AI foundations with simple Python. Probabilistic forecasts give you a distribution, not a single number. That matters when downstream decisions or stakeholders need to know how confident the model is. Two common scores show up here: pinball loss and CRPS. Pinball targets a single quantile. CRPS looks at the whole predictive spread. Pick the wrong one and you can end up rewarding models that look good on paper but misrepresent risk. Think about a demand forecast where you must stock emergency parts. If you only score the median, you'll never notice the model is overconfident or wildly uncertain. The metric should match what you actually output. If your model emits a 90th percentile, evaluate the 90th percentile. If it emits a full ensemble, evaluate the ensemble. That simple alignment makes model selection honest and cuts down on surprises. Pinball loss is asymmetric. It punishes under and over prediction differently depending on the quantile. CRPS is broader. It measures how simulated draws match the observation across the whole distribution. In short, pinball is sharp and focused. CRPS is holistic and cares about spread. Use pinball when you commit to a specific quantile, and CRPS when you produce full samples or a CDF. We'll build a compact example so you can see all this in action. A point forecast, two ensemble forecasts with different spreads, and two candidate quantiles. Then we'll score quantile forecasts with pinball and ensembles with CRPS, keeping the tracks separate so nothing gets mixed up. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we start by constructing a tiny toy dataset and two synthetic ensembles so we can see the differences clearly. This snippet creates a tiny NumPy forecasting setup where a point metric sees only the center. The observations live in Y. The point forecast lives in point. And two distribution forecasts, tight and wide, share that same center with different spreads. NumPy broadcasting in point.none makes each row an easy-to-read mini ensemble around the point forecast. The point MAE score is useful, but it cannot tell whether tilt or wide uncertainty is better. The visible output shows the point error baseline that both distribution forecasts can hide behind. Our point baseline is informative, but it won't tell us which uncertainty shape is better. Next, we implement pinball loss so we can judge quantile forecasts on their own terms. This example implements pinball loss in NumPy for one upper quantile forecast. A point metric treats misses symmetrically, but a 90th percentile forecast should be judged by whether it behaves like a high quantile. The pinball function computes error, then uses np.maximum to apply the asymmetric penalty controlled by tau. Here, Q90 is too low for many observations, so undershooting Y is expensive at tau equals 0.9. Increasing tau makes underprediction more costly and overprediction less costly, matching the behavior expected from higher quantiles. The output shows the quantile-specific loss, not a generic point error. With pinball working, we can line up candidate quantile forecasts and see which one actually behaves like the claimed quantile. This code compares two candidate 90th percentile forecasts with the same pinball function. The low forecast often falls below the observed Y values, while Q90 safe sits above them more often, which is usually what a high quantile should do. The dictionary Q-scores keeps model names attached to their computed losses, and min selects the candidate with the smaller score. This is a small but important workflow shift. Evaluate a quantile forecast as a quantile, not as a point estimate. The visible output shows which quantile forecast wins and the loss behind that choice. Next, we switch to full distribution scoring. If you have an ensemble, you need a score that inspects both accuracy and spread. That's where CRPS comes in. This snippet scores the full predictive distribution instead of one selected quantile. CRPS rewards draws that land near Y, captured by miss, and also accounts for spread through pairwise draw gaps in gap. NumPy broadcasting creates all draw-to-draw differences per row without loops. So CRPS sample works on the whole in-memory ensemble at once. Unlike pinball loss, this score uses the entire set of draws in tight or wide. The visible output shows that the tighter distribution is preferred here because its uncertainty is closer to the observed outcomes. Finally, we combine both evaluation tracks, so each forecast artifact is judged by the correct loss. This example turns the scoring choice into a tiny artifact awareness baseline. Full distribution forecasts go into dist scores and are judged with CRPS sample, while 90th percentile forecasts go into Q scores and are judged with pinball. NumPy's NP quantile extracts a Q90 candidate from wide, which makes the contrast clear. A distribution can be scored as a distribution, or one extracted quantile can be scored as a quantile. The book's dictionary keeps those two evaluation tracks separate, so the final selection does not mix incompatible artifacts. The visible output shows the selected distribution forecast and the selected quantile forecast side by side. In a real project, you'd replace these arrays with your model outputs and logged observations, and enforce the rule: quantile outputs pinball, ensemble CDFs CRPS. That keeps evaluation honest and prevents rewarding an overconfident ensemble or a mislabeled quantile. The takeaway: pinball evaluates a single quantile. CRPS evaluates a full predictive distribution. Use pinball for trained quantile outputs, and CRPS for ensemble or CDF outputs. And watch out! Comparing a quantile directly to a distribution with the same metric mixes incompatible artifacts and can mislead model selection. As a practical next step, rerun this pipeline on a real dataset such as the M4 hourly subset and tune the quantile tau or the ensemble size, so you see how evaluation rankings change with more or fewer draws. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.